everyone to today's seminar. Our speaker today is Professor Xin-Zhong Liang from University of Maryland in the Atmospheric Sciences Department. Dr. Liang did his PhD at the Institute for Atmospheric Physics in Beijing, and then he came here to Stony Brook at ITPA for his postdoctoral studies, and he was here between 1987 to 1990. Subsequently, he worked at the University at Albany, and then Illinois State Water Survey, and then he became a professor at the University of Illinois in Champaign-Urbana. And then 2 years ago, he moved to the University of Maryland with his very large research group. So there is this idea that that different climate models should be compared because they are trying to simulate the same system. So there are many different models around the country and around the world, and if you run them with the same boundary conditions and with the same solar constant, they should get similar results, and the differences between them can be used to diagnose model problems. So this idea actually originated at Stony Brook University, and when Dr. Liang came here, he worked with Bob Sess and their other colleagues, and actually did the first intermodal comparison project. And I remember they published several very highly well-known papers, 2 of which were published in Science. And subsequently, after he left Stony Brook, Dr. Liang has focused on improving regional climate models. And he has been amazingly productive. He has more than 110 papers on regional climate modeling and their applications, improvements of many kinds, and so on. And so today he's going to speak about one such work which he has been engaged in recent years, and that is extending the WRF model into the climate mode, that is running it for longer times. And he has applied this model and other models in many very well interesting applications, like the impact of climate change on air quality over North America, or on crop distribution, and etc. So, and maybe he will tell us more about it. So let us welcome Dr. Liang.
Thank you very much.
So should I lower the light?
Yeah. Is anyone can see it clearly?
I will just lower it.
Okay. It's really a very warm feeling came back after almost more than 20 years. The first day when I start here, and at that time, Bob Sess and Professor Ami was there in mechanical engineering. So 1987, when I came here January, I remember I only have $50 with me that time, and that's really true. Only China only allowed $50 exchange at that time. Then I was stuck in New York consulting because I don't know, that happened to be the record snow. And all the railways been stopped. The only thing you can get here is by truck, by the car, but the car is not driving on the snow, heavy snow. So I don't have money. I called the consulting, happen to have a friend there, and he said, I give you 1 day boarding free. And then the second day I have to go here because I don't have money. I call Professor Zhang, and at that time, and he said, Liang, don't worry, you get on the bus. I will waiting at the bus station to pay the bus driver. I did. So and then the second day, I pack my big bag with all these books I bring, because I'm supposed to come here to build the IAP's 9-level models at that time. So big bag with all these books and material, and walk about 1 feet of the snow. Here take about 1 hour, get there. I don't have bring the boots. All my sneak is flood off with the snow when I get there. When I got to the mechanical engineering, sitting on the step, all the doors are closed. But I don't know that the snow will be closing the door. So I'm waiting there and thinking about what is this the first day to do. And then came Professor Sess, and the Professor Sess driving his small little car. He said, "What are you doing here?" I said, "I'm supposed to get into the building, I don't have the key." And he said, all the buildings are closed. So he took me back to the house. So that is my first day of the US. And I think that is some memory. But anyway, this is a very good feeling to come back. So now, I started with the global models. Actually, China's first general circulation model is my PhD thesis. So it's currently still used for their seasonal prediction. And the second generation of the multiple layer GCM was done here with Bob Sess, and that's still now is part of the IAP's global model circulation. So, but I didn't benefit, and after I finished my PhD, I immediately got here. Actually, the second week I was flying over here, so I didn't even publish a paper on these models. So now, after 10 years here and another years in Albany, I shifted to the regional climate. This is called by Illinois State at that time. They tried to understand what to do when the Chicago O'Hare Airport is going to expand. And they have many issues to deal with. They need to build the traffic, the highways to the airport, and they already have claims that when you have the highway built, what is going to do? Because the property will be damaged, because they have to de-icing it, so a lot of ice will deposit on the property, and the state receive many of these claims that you need to, my property value is down and you need to pay for it. So the Illinois state also have another problem, is the hypoxia issue in the Gulf of Mexico. And many of the hypoxia area, the coast, they sued the Midwest farmers that you are to put too much fertilizer in. And that's really true. The average of the best fertilizer should be about 125 pounds per acre. But farmers, however, they put about 1/3 more on top of it for security. At that time, when I start working on this problem, we don't understand why farmers do that. After a while, when you see the farmer house they suffer, you will see why. Farmers, they have their land, but they do not have the money to put the seed on. They do not have the money to buy the fertilizer. So what do these farmers do? They contract these land to these big shops in New York or in Chicago. So actually, these are the guy is planting the crop. So they will not oversee this how the crop being grew. They came by in summertime and springtime to see is this piece of the land I contract is look greener than other. They don't care about what is happening. So these farmers, they want to make sure that I put enough fertilizer, because that time is cheap, that will make them appreciate that my farm doing better. That is exactly the cross sequence we have to deal. Because of this complex problem, establish so-called establish an Earth system model to deal with this impact, and that is what I end up with doing that. So this is making a long introduction already, but today I'm going to using the Seawolf talk about more about how I develop the Seawolf and focus on climate prediction instead. So this is a system, not just the Seawolf. Seawolf is a core component as one. And then gradually, originally I started with the CMM5, but for the last 10 years, work on the Seawolf. So we actually use this system to get more application. You can see there's no money really toward developing the core. All the money I got is through pieces of application. So we got pieces for EPA assessment starting from 2003. I still have another 2-star project working on with EPA on water quality and the black carbon assessment. And that one is basically using the global model, which I familiar earlier, but we have using the regional climate model as a core to driving these air quality CMAC, which actually started with Julius Chang when I started in Albany. And then you need a lot of observation, but now working on the water quality, it's much more because you need the air quality come in, but then you need to also build this dam operation. Many of the manual or the human dimension have to be into the system. And that is going on. So the system became bigger and bigger. But I will focus on the core component of the climate. So what I'm going to talk about today is why will the regional climate model research development will continue. And this will be very short because I can talk this for a long time. What is the Seawolf? Relative performance to relative others. How does the Seawolf solve the challenges we need to meet? There is one problem we need to, of course, the scale and regime dependence. And the physics configuration, we have a lot of them, and why I put so many. And optimize the physics example, that's because we build for this purpose. And I will show how this will actually make sense. And then, of course, the system uncertainties. So how much does the skill the Seawolf does have? Because if otherwise no skill, there is no point. It's have stuck with a team of over 10 people for 10 years work. So this is a lot of commitment. I will show you some of the examples. So we end up with writing this BAMS paper. This took us about 2 years. Actually, the review process is originally when you're writing a proposal for the BAMS, it takes about 1 year to approve. The reason this is that there is already NRCM, NCAS regional climate model. Why you need have the Seawolf. And there is also the other regional model, the RAMS, why you need this. So we have rebutted the letter is very long, but finally they said, oh yes, your Seawolf is unique. So finally we get in and we published with this color illustration of that feature. So I'm that done. So what the regional model do? As a global, you don't have a boundary. For regional, you do have the boundary. It's a bad part of it, or it's also a good part of it. Good part, we can separate the large scale versus the regional, so we can make more on the regional problems. So in our design, we very strongly believe that the lateral boundary condition should only come from the lateral boundary condition, and we strongly believe that the forcing term for the regional model should not including the surface. So we make the nudging coefficient near the surface close to 0, and actually only start from, for example, 850 above. We believe that large scale circulation should be forcing all the other portion should let the regional model develop themselves, take advantage of the regional processes. So we do not have spectral nudging inside of it. And that actually makes it very difficult constraint for you to develop better physics to get these results. Okay? So when you that means all this lateral boundary condition from global only and then. But we need to make the system very robust inside. So give you the first look at the brief general idea of how good the Seawolf currently is. So this is a monthly continual simulation. Just want to warn you a little that the Wolf, when you run continuous, it's a big problem. There is the restart issues you need to deal with. They cannot be bit by bit restart. And the Wolf can also run trouble like they have to restart several times, maybe a week or a month, restart because they blew up. And I have reviewed many of these papers, run the Wolf on the climate. There is a lot of issue need to deal with, so we spend a huge effort to solve the restart issue. So now we can restart bit by bit any place And this is a continuous run. We didn't stop anything. And so continual run for 30 years without any blow up. That is a very assurance of the quality for climate simulation. So one of that I show you here is a monthly simulation, compare the precipitation on the monthly mean. The top is the Midwest area of average, and you can see from 89 to continue, and now I think we have already continued 2012. And another is a cascade, and you can see this way in the Midwest is a lot of massive processes going on. And actually, the reason I didn't publish any paper within the last 10 years on Seawolf, because I have a very strong rule imposed by Illinois State Water Survey. They said that if you do not get the Midwest right, don't publish. And I publish the other things, of course. But finally, we get the Illinois State, Midwest very close to what originally I pushed. I have a CM5 done well, and this have to be passed better than CM5 so I can publish. And that's one of the reasons. And over the cascade, you can see the observed and the model almost cannot be separated between them. So you can also look at the daily variation, because we are not just satisfied with the monthly. And you can, I show you just take one piece of the 1993 flood case, so you can see the daily precipitation also matched very well. And when you go to the cascade where the terrain is the driving force, the model actually matches so well. I think some of you may recall there's several papers talking about this. Wolf is overestimate in the terrain precipitation over a cascaded region about 20, sometimes 50% more. But actually, in our case, we don't have any like that. So now we also need to deal with not just the Midwest, but need to deal with the coastal ocean as well. And I think this will be interesting to this committee. So one of the paper, my PhD, she just finished defense last week. And that is talking about how to deal with the coastal ocean problem. And I do not have time to show it, but just want to give you a quick overview, review of that. For example, we know the Midwest problem. So this is ERI, the ECMWF, their in-chain analysis, and their product is very, very light rain compared to the observation in the Midwest for the 2008 MTT's flooding case. This is the ancillary analysis on another end. Their model always persistently have heavier rain than normal, particularly in the south, and all these. So you can see it's very dramatic. So what we do is we take the ERI's circulation upper channel as a lower and upper channel, so not near the surface, to driving our Seawolf, and this is the result. So we have solved this, getting better, but this is still improving. Next, I will show you how better now. And the important is to look at over the coastal band. Actually, this systematic overestimation in many regional and global model is now, in our case, is solved through many of the work about cumulative parameterization. So you can also look at the differentiation in the different component, particularly the extreme event. The regional model is developed for capture these these extreme events. So show you here is one example of the 1993 record flood. I think everyone knows here the 1993 flood in the U.S. This is 100 years record flood Midwest. There is a big loss. That's one of my part being called in, because the 1993 flood is causing all these levels in the Mississippi. The level is too high. All the cargo have been lost work for almost stuck work for 3 months. And another is 1988 drought, and the water level is too low. The cargo stopped about 4 months. And that total loss, like each is about 10 billion or something of the loss, including the agriculture. So this is a test bed. So the 1995 case is that it's a mean, summer mean, and the number of rainy days, and you can have a rainy intensity and 95 percentile, because this is extreme heavy duty is more important. This is ERI, as we said it's earlier, they are relatively light, and they are mostly is giving you very frequent rain days. And then you can, of course, the intensity is lighter, and the 95% is that. When we use the ERI's circulation information, not the precipitation, to drive the Seawolf, this is the quality you are getting. Is have a much improved results.
Just
Yes.
a question you may talk about it later, but what's the resolution you're running at?
30
What's
kilometer.
the domain?
30 kilometer, the domain is bigger than this. It's a North American domain. And we have 2001 paper specifically deal with how to choose the domain. The domain choose is very, very important. I spent about a year to decide where the domain is, because particularly try to get the largest scale circulation driver to the domain. It's a very important topic. Okay. So now, what if my effort for a 10 years effort, it turned out to be another kind of regional model on shelf? I probably will get in very trouble. So that's also another requirement the state agency always ask, is your model better? Because they spend money. So I will show you some of that using everything the same. Everyone is driving the same reanalysis, and then we compare the seasonal variation into any anomalies, extreme events. That paper almost finished, but there is many conflict of interest. These people have not been published. But I will show you here. So let's compare. There's NORCAP effort. NORCAP did a wonderful job to put all these many different regional models together with different driver, and that they done a wonderful job. So we put their model, taking it, for example, CMM5 is mine. I didn't participate in the NORCAP because we don't get funding. And the agency do not allow me to if I don't have the funding to do so. So I have put myself CM5, that's earlier version, and the Seawolf is the red. And then you have the CM3, which is Filippo George's model. It started with Ankai also, and now it's in Italy. And the Hadley model, the Hadley so-called unified model 3. And then the ECP is NOAA's spectral model nudging with the spectral model, and another the Canadian model, and also the Wolf's model. There is two groups I'm showing here is the frequency for precipitation. So what does this frequency mean? I take the monthly values of each grid point, compare with observation at that grid point, do the correlation, you get a correlation for each point. And then put all these grid correlation in the whole US as show the frequency distribution. So that will give you some systematic information about better or not. If the frequency distribution for correlation is toward 1, that you will give say it's better. Relatively, these categories toward 0. So I compare, one is the frequency precipitation, another is surface air temperature, and another is shortwave radiation downward to the surface. There is 2 branches, basically. One is, here is this is winter. This is for the spring, summer, and the fall. So now, there is 2 branches. One group of this is systematically lower than another group, which is systematically higher. So what does this 2 group mean? So I have 2 models, the Seawolf and the CMM5 is in this group, so with a higher performance. But then the other originally have been available now, only from the NORCAP, only 2 made up to this group. that two model is, one is the ECP2, which is spectral nudging over the whole domain. Another is the Canadian model, again, the spectral nudging plus the wind convergence nudging to that. So I think you can calculate yourself. When you nudge the moisture convergence itself, on the time scale of monthly mean, you will know where the water goes. It must go to rain. So that is where you can get the monthly value. We do not use spectral nudging, so we focus more on the physics. And also, you can see the temperature all the same. And more so is the short wave, the peak, and this is very important for the work we have done later on our shot. So what these model results tell you is not really, you can say the solution is a problem, domain design is a problem, all these many other things can go wrong. But the most important thing is how to get your physics fitting to the scale you are interested. That scale dependence is the most time we spent for the last 10 years. So the history is actually running the Seawolf starting from 2002. And there is many papers published not directly use the Seawolf end results, but more the different component to it. And this is not supposed for you to read, just to say that we did work hard on this physics processes. So the principle of the Seawolf development is we want using the carrier name wolf, and it's basically it's extension of the wolf. So whatever the wolf currently can do, we will inherit, will not violate. That means that we will build the climate first based on the weather need. So we refer back the climate defined as the statistic of weather. So we want to make sure the weather is done right before we get the climate right. And that can help us to take all the effort have been worked with the wolves with a big community. Actually, I involved the big community in the very beginning. I was also the physics team's group. Then we inherit also the wolf's idea of many physics, just like the method scale. But what we really do for the last 10 years is work out, actually day and night, to make sure all the physics really work plug into play. That's not really the case in the wolf, if you know that, okay? But that's a lot of effort to deal with. And we've done that, so we make this all the physics. And we currently, and also not only original physics, but we including many other physics we feel it's important for climate. And I will show you a few of them later. And then we also call that the system is developed not mean for me to play in just the science. Also, there is a responsibility to deal with the funding agency like a state, to deal with the society. So we have to deal with the agriculture, because the Midwest is important there. So we have now have a crop yield particularity. We need to deal with the coastal ocean issue because of hypoxia issue, and we need to deal with the lake. Great Lake is under our watch, and level the water stream. So water quality, air quality, the Chicago, and these are the crucial area. So again, we build many of the different components. So given that, we have, see the physics options, this is already pretty old. And if you can type Google, say just a Seawolf, and the first website will be this website we'll talk, http://seawolf.umd.edu. So there is quite a few here. And these are the physics we have already older, we have many more. So if you look at the cumulus parameterization, we almost have every cumulus parameterization we can handle the, if I send an email, I constantly send an email to other people, they ask for, hey, I read your paper, this is a great paper, great humus scheme or great whatever PBL scheme can they deal with, and some they do, and we put in to make sure it works. So one component cloud aerosol radiation scheme currently is the biggest example we can have. So total, I will talk about later, basically do all the global and regional models, anything to do with the cloud radiation aerosol we put in together. In order to make the system work, the biggest effort actually, you probably don't believe me, is the surface boundary condition. And this is still is the bottleneck for the Seawolf general, even though I have publicly released, but this part have not been released. And even now, I have a big team working on this, because for the past, we're using pieces, combine the GIS, use the GIS information, use the fortune, use a lot of these put together a package, because the component is so complicated. And now we have to make it more unified, like one click and for everyone to use. So still working on it. So you have the terrain, of course, this is just a few. We have the bedrock of the lake and the rivers, and also like a coastal lines, have to be resolved very carefully, and also these. Just believe me, this is a very headache work. One show you here is for the Chicago urban area. When we want to simulate air quality, we found that GIS give us a position, put the Chicago on the Great Lake. And we spent a lot of time to find the why. Finally, we find that the radiance being used in GIS is actually, at that time, was very hard wired inside and we couldn't change. And then finally, we find that bug and solve that problem. So this is a lot of problem. And for the sand and clay, for example, if you want to get the terrestrial hydrology right, the sand and clay information is so critical. Another way is the bedrock. But where you get the data? There is no global data set for that. The only one currently used, even in the world, called FAO. But FAO is based on, for example, China only provide 150 sites to the FAO. US is approximately about 150 sites. And for hydrology, we're talking about inch by inch. We really getting bad. If you blame that the model is doing bad, should also start blaming that we do not have the data for the model to use. So we spend a lot of time to get the data sets, including the bedrock and the sand, the clay information, and even, for example, the lake depths or the Mississippi River, we don't have good data for the depths. But we do build these now, and we have very detailed stream flow in the system. This should be the same. The first system actually in the world now really couple the 3D hydrology to the atmosphere in a coupled way. And we have crop yield, for example, this is cotton belt, the soybean and corn belt, and this is a cotton belt. All these have to be archived in the data system. So now, after you deal with these boundary conditions, the fundamental issue, of course, go back to the physics. And only assume that I've done the other part, the hard part right, then we spend the time on the physics to make sure the physics is also right. So there is issues to deal with is what kind of model physics we need and how we're going to improve it. And all these skills actually depend on the scale we talk about and the climate regime. And believe it or not, there is no particular scheme work all. So the climate regime is the part probably we have to work with our scientists for a while, probably at least in my lifetime. So what is the hydrology deal with? In the past, the people using runoff to categorize what the water came to the surface and how much they can hold or penetrating into soil, then the remaining part, they will run off. But actually, we need to deal with, when the high resolution import, you need to deal with the run off. That means everything run in the grid, they will penetrating again to the deep soil and recycle back. And that idea will require a 3D hydrology concept to deal with. So we published in 2007 regarding how we're going to using the 3D information to make better prediction on hydrology. So we introduced not only the vertical flow, but also the lateral flow. Think about one simple idea. When you walk on the hill from the top to down, you will see that the soil moisture at the surface will be drier in the hill than in the valley. That is what the simple idea is. So that means that the soil moisture itself at a higher resolution, they have a very strong covariance with the terrain height. But that critical information never been put into the hydrology before. So when we including that covariance, so originally you only need to deal with 3 terms in the hydrology component. But now we needed to deal with 12 terms in hydrology and parameterize the covariance. And that is the one shown here, significant impact, particularly in high resolution. I show you here one is we start with common land model. And each of the top show you here is the precipitation you're giving. And this one, the bottom show you is the stream flow. And you can see that the observed is this circle mark. So each time when you have the rain, the common land model, which is also part of the NCAS model, they give you false alarm of flooding situation. Just too much of the stream very quickly run out. But only when you're including these high resolution information, now the green one, they capture the recession curve very nicely. And actually one of that I didn't show is that they were found that even with the hydrology, we have 2 stations nearby Mississippi. It's a very odd performance. We've done beautifully in summertime, but on the summertime it's not. And we end up finding the dam operation being taken care of. In the summertime, they flood out, and in the wintertime, they close it. And that's lead to what currently I'm working, the dam operation I will show in the last slide. So when you do that, then you compare the Illinois state waters, soil moisture measurement, long-term measurement, and you can see that for the long comparison simulation from 1984, the biggest problem is that the original model, for example, common land model, all these, at that resolution, they do not have a strong seasonal cycle. That means the soil moisture almost flat throughout the year, throughout the months, right? So that response is not kicking off in the coupled system, and interannual variability also there. So when we including these 3D hydrology, we much improve the observed and the model match very well. Yes?
It's clear that local weather is going to affect the hydrological flow. Do you have any evidence that the reverse is true, that evaporation and so on needs to be taken into effect to get your weather predictions correct?
This I think is I need to work on, but I will show you one plot how the coupling between the two. Good point. So this is the one. I think many of you may know the so-called hotspot coupling. The hotspot by many of the coastal ones, for example, coastal, and there are people talking about the hotspot is running, for example, the transition zone between the drier zone or drier west to the wet east. And these transition zones have a very strong coupling between the precipitation and the soil moisture. However, this is what we show from, I'm showing here is a correlation between the Seawolf's precipitation and the soil moisture of top 2 meters on winter, spring, summer, and fall. And this is where Wolf been done using the same concept and run it. The Wolf coupling is very weak compared to the model. So this is currently NOAA's operation, NOAA, N-O-A-H, being also the default part of the wolf. Actually, this is the most complicated one in the wolf. And the NOAA uses the NOAH to the weather prediction. So this is now the NOAA is paying much attention to this. When I show them, their coupling is totally off compared to what the people are thinking of. So there does have an important, but I didn't do the weather forecast directly. So then the cumulus. I know you guys in Morocco have done a lot of superparabolization, and that's the way to go. But for the climate, we still, I think, take a while to run that high resolution program. And in particular, when we deal with the Earth system, we need to run huge amount of example I will show you later. So what we still work on the cumulus parabolization. So when I compare many of the about 14 or 15 different cumulus parabolization, when we decide, and I will show you, not show you the results. If you're interested, talk to me offline. Then we use the so-called ensemble cumulus parabolization. The idea behind is that we only use one cloud model. So everything, the conversion, the chain, in chain, all these will be the same. However, we do agree, because the closure is the number one problem, as we found from the sensitivity analysis. So we use all different kind of closure you can think of. Currently, you can categorize 5 different components, which actually is not my idea. It's a very brilliant scientist, George Greers. I worked with him very long time and get this work. So that idea, they separated its quasi-equilibrium, Karl Schubert's earlier, and the moisture convergence, Krishnamurti's, and there is called work function tendency. Tendency means it's the changing, the positive changing, and also the full called work function, the cape removal, and also the vertical velocity. And we will focus this more, I'll show you why. And each of them, they have very different variation of them. So the total you can came up, at least now, we can to 160 of them, different closure to deal with. So in George Greer's idea, published in JAL 2007, that is actually the average of them together, but that is not work well. So that is a presentation. I just show you one paper seem to be very, it's already finished. I just want to take advantage of starting April, the bank, the AMS, we're not going to charge the color page. So I'm asking my student to stop. Otherwise, this paper will cost another $5,000. That's a cheap scientist can do, okay? Anyway, this is to show you the 1993 Florida again in the summer, and this is observed. This is ERI, the best in analysis from European, and this is the two only thing change in the ECP in the Seawolf is the closure of that skin. Not put all of them, but I choose one at a time. Show you here. This is the moisture convergence. This is use the vertical velocity, and you can see. For the convergence, there is big issues in North American monsoon, in Florida, and also in the coast, which I done over the ocean, marine. I didn't have the time to show. They overestimate, as many models have shown. So the moisture convergence at these regions happen to be a problem deal with the numerical. So in these places, there is plenty of moisture. You can see the sea breeze. You can see the terrain, the the terrain driving the force, the sloping. All these actually have plenty of moisture conversion, but that not tell you they trigger the convection all the time. So when we use the vertical velocity at the cloud base as a trigger function, yes, we solve this problem very, very well over. So we have much better solution now over these coastal areas. Another component is regarding the uncertainty we have deal with in global model. And actually that started with Bob says, that it's called Fangio. He loves sports car. And the Fangio, I think, is a driver of one of the driver in Italy. It's very famous. So he named the first intercomparison of the climate feedback of Fangio. I was very lucky to be part of that. So Because of that, so now we take every radiation package in the world we can have. We have ECNWF, we have ENCA, CFDL, Canada, Australia, UK Met Office, and CFDL. All these put together. I work with my staff for 5 years to unpack everything, just piece by piece, just like a bone and meat, everything separate. Then the first thing separate is the 3 component. One is the radiation transfer alone, another is a cloud, another is aerosol. After this piece of work, we put them further. The cloud, for example, we separate to cloud cover, optical, the cloud particle size distribution, for example, and liquid water, or the overlapping, or the opticals. So now we have everything what other model or some is not in the model already published in literature, we can easily port into the system. Then we put them together. So that effort, and we can now running actually 10 to the 18. So don't be shocked that is that a human being cannot do, but that's fine. What I meant here is trying to see that there is a lot of different way to deal with the cloud aerosol radiation. But we're running the idea on the blue water, the biggest supercomputer, to pin down the uncertainty that addresses IPCC's climate sensitivity. And I will show you one of the results why it's important. This is supported by DOE. Okay? And one of that is show you I couldn't run 1018, yes, but I can know the statistically how many of the gold scheme have been used physically in these big centers. UK Met Office, Canada, all these part of the IPCC. Then choose about 960 of them to combine them. So now in the past, you only have 23 models to work with. Now I have 960 to work with. So now when you run through and you compare with observation, I show you here is the frequency distribution of that 960 simulation with the observation. This is shortwave radiation at the top. This is long wave radiation at the top. And this is shortwave cloud radiation forcing at the TOA, and this is TOA long wave cloud radiation forcing. And the vertical bar is the observation uncertainty. Yes, for different satellites, 7 of them, products, we have about 10 watts per meter square still uncertain. But that uncertainty does not explain what the model spectrum is. So model actual spectrum is about 70 to 80 watts. We are talking about monthly mean at the global mean over the whole planet, 60 watts uncertainty. Much bigger than current IPCC have shown us. So that is what the next one we will see how that uncertainty will lead to the climate sensitivity. Now, it's not just fun to put all these physics in one model. It has a very targeted reason to do so. That is, we believe that every scheme has their benefits and their deficiencies. The God created the universe, we do not really know. We, as scientists, only try to understand piece of it. And we have the observation measure the only piece of it. So that's why we have uncertainty. So now every science product, like the cumulus parameterization, or any schemes we build upon these very, very limited observation. And it's also based on very limited knowledge of specific scientists. So combine them together, there is no universal solution to the nature. So all the schemes we so far have, they only can be applied to certain regime and certain places. So in this idea, it's not actually came from me, it came from the very profound Professor Krishnamurti. He wrote the first paper in 1999 in Science about the enzyme. So now, when we do that, I demonstrate in the first, at that time they use multiple model, not multiple physics. So I do that in 2004 GRL, and show that if we use two physics schemes, and actually that result could be totally different. I shall demonstrate here is taken from that paper. This is observed 10 years rainfall precipitation over the US, millimeter per day. And this is, I trained in my model only the Cambridge scheme, cumulus, and other is Greer scheme. And that cumulus scheme, they too have a very different response. You can see that the Cambridge makes the precipitation much overestimate in the south. Okay? And this one is very lighter precipitation, but done very beautifully in the Midwest. If we are combine the two together, this is what optimization can provide, so, or compare with observation. I use cross validation here, show how good the prediction can be just by two. And when you trace back the physics behind the two cumulus scheme, Cambridge is based on the Cape instability. So that Cape instability is mostly being captured in the sensible heat and latent heat in the south. But this one is based on convergence or the tendency of that. So the physics, they are not the same, but so they are combined together. So now, that one is carried over to the Seawolf. Okay, the Seawolf now you can, now we had afford, at that time only two, now afford 32 of them. So we put them together. There is two important issues here. Again, this is the frequency distribution of correlation over the US, and this is the frequency distribution of the root mean square error of precipitation again. So for the 32 of them, most of them you cannot distinguish overall performance over the US. They're almost similar. So only two, one of this light is happen to be all from the cumulus scheme global model they use, including NCAR, CSU, GFDL, and the TDK for them. The global model, because their concept on the cumulus will be different on the regional, like this all the regional model. So now, but even then, there's still not difference. If we are going to average this 32 runs together, don't do anything, just average them, this is the scale we're talking about. There is a substantial increase. If you just look at what the weather has, say, you improve, you improve that magnitude. Will take a human being about 5 to 10 years of the research. Again, that's a huge increase of CPU. If we further to consider each scheme has a merit over a certain region, then we optimize the weight for each individual. This is where we will end. Optimize the solution will make us, at that time, we probably end up with have the scale for the precipitation is close as the temperature at the moment now. So that is our dreamland to poach, and I'm working very hard now, try to make this curve go to this way. This is more ideal the case we want to chase. So there is a lot to do with optimization of the physics. Okay. So now, by now, I hope I already gave you the answer that the Seawolf success is happening. It's actually we've done a lot. We do not probably favor using the downscaling. We believe the Seawolf is developed with detailed physics at regional to local scales. These advanced physics represents a crucial factor that enables Seawolf to do better. Okay? So now this is to the reality check. So when we are now running the Seawolf, and we hope to run the operationally to the seasonal interannual prediction. So we take the NOAA's operational forecast and CFS and as a driving force to do the regional prediction. So when people we finished in the GRL 2001, This is again the root mean square error of the precipitation millimeter per day. This is from CFS's prediction for the winter case. The real time 0 months, 1 month, 2 months, and overall. And we use the CFS again, the circulation, to drive this bound as a letter boundary. This is what the Seawolf get. Systematically reduce the root mean square error. But for the weather part, people are more interested in so-called ETS score. Okay, the ETS score is as basically called equator thread score, and it will show you the different bin of the precipitation, checking the extreme event. For example, I shall you continue from 82 to the 2008, I believe, and then this is the bin of the precipitation strength. And you can see this is the difference between Seawolf minus the CFS. ETS score equals 1 means perfect prediction. So that difference, we are talking about negative 0.4 or positive 0.4 above. So that's a huge difference there. So let's take a look at these. So the major gain in the Seawolf is the two extreme. One is the light rain with substantial improve. Also, the heavy rain, substantial improve. These two parts actually now is the biggest hit for the agriculture or many impact sectors that we want. So this is what the purpose. Our regional model does get these right. For the middle part, we didn't improve too much, but did not change too much as well. So we are happy with this result. When I send this paper, it's only take about 1.5 months we publish it. And then the one review asked, Liang, this is luck. Probably it's your luck, only one model. Can you show? They say this is not required for this paper. Can you show the curiosity that this can be do for other model and other season? So after that, we've done that with ECAM. So you take the ECAM, the II model, and run it for all the years again and all the season, and the difference you can see. This is winter, for spring and summer and fall. Again, this is ETS score difference between the Seawolf minus the global. We do improve significantly. But there is a trouble making here. This part now is solved. This is actually through the southeast U.S. At that time, beginning this version run, there is a huge precipitation involved using moisture convergence. Now we use vertical velocity, we solve this problem. And we are working on the paper to be submitted. So that will be soon, hope finished soon. The Seawolf will include the advanced physics schemes is crucial to climate, and we couple this essential component directly linking to the impact and built upon a suitable example. And this actually is very unique to use and for skill optimization, and has a greater capability so far. And now, this is the current trend I'm working, lead my team to work on. Try to include as much possible the human dimension into the system. This one is already done. We are working on the paper talking about the human management of the water resource, including agricultural irrigation, and also the dam operation. So shall we just one case here with or without dam operation? This is without operation already makes the scale 3 times bigger than the observed one shown here. So very tremendously problematic, cannot even use. With the dam operation and irrigation system, we can now nail the observation for the stream flow in the red level, for example. So I'm closing here. See that the Seawolf can be used many. One is particularly for the student. We can use it for research and develop a test, evaluate physical parameterization. Believe it or not, you can run the Seawolf at a very high resolution and get parameterization going. We can improve the weather forecast, and one of the students using the same methodology, same model, but in China, operational to use they only can run 8 examples of the physics, and they use the past, the week's performance error to weighting the example for the next week's prediction, and done beautifully, the skill enhancement. I don't have the time shot. And then you, of course, can project climate change and the impact. That's more called, and thesis research. Many of my students actually using the Seawolf. And just fun. Thank you.
So let us see if there are questions for Professor. Yes, Kamazima.
Yeah, the question I had in the very beginning, you showed that summer seems to be a problem to predict. Why is that?
Okay, the summer is a problem because the convection is the biggest problem. And the moisture is also the biggest problem here is. And particularly in the summer, there is no dominant process. Because in the winter, the large scale circulation is very dominant. Okay, and then the inside, for example, in the Cascade region, doesn't matter how you change your physics, as long as the physical consistency in energy all is done, they done beautifully. But in the summertime, the local and the regional scale process is so important compared to the synoptic scale. So if you don't deal with carefully in the regional model, you will get worse result than the global model.
Would that translate to tropics?
Yes. So one project currently working with Singapore and another working India is running the Seawolf for monsoon. And I didn't show you here. This model have much better skill enhancement over China domain than over US. I'm very sorry about that. So this is not my purpose. Originally developed, everything is done in US. But the results, like so far, we didn't publish any results yet. But the results for 1991, 1998, from all these, no model can predict these events. We done beautifully. And also, you may recall the 2000, the last 1 year, the Spring Festival, the hit. I couldn't remember the year. The whole China is going crazy because the freezing rain and causes the traffic jam, everything. The only model predicted that event 120 hours is the Seawolf optimized physics, and we have a paper talking about that. So again, this model have very good performance about the monsoon because that system have so many different frontal system and all these activated, and that optimization made very well.
Yes. Shuaiqi, do you have?
Yes. Maybe I didn't understand quite well. When you talked about the boundary condition, you mentioned that there is no surface boundary condition.
I mean, there is a surface boundary condition in the model, of course. So we have, what I meant is that there is a lot of trouble to find a good surface boundary condition. For example, where you get the the top 10 meters soil information, there is no. The US is about 2,000 stations being drilled over the US for 20 years record. Okay, that 2,000 drills, they only penetrated to about 150 centimeters. And some over the West only penetrated to about 50 centimeters. In the China, they drilled about 20 years, they drilled everywhere. At that time, China is short of the food. So they drill about 9,000 wells in China to get this soil. But that soil in China, they will not release to anyone. Even now, I have to work with others to get that data information. For Africa, for the Canada, all these places, we only have FAO to work with. For that, this is just one. Another is if you look at the satellite data about LAI or EBI alike, the difference between the two, I published one paper in the EI 2005 talking about that. The difference of just the sample as you consider as a live area index, which can be about half or 50% difference between two satellites, if each are or modest. So we have to go back to the field in Champaign to verify which one we can trust. And we found that the crop is systematically being underestimated by models. And that when we use the field to check, we have to pump up the models information to be consistent with others. So again, there's a lot of holes being dealt with. So recently, models released the new data sets, and we upside down again because the LAI value is changed back to higher. So then have other problems to deal with consistency. So we end up with writing another paper. That's probably good for writing paper. So we find reduce the whole surface boundary condition consistency, including albedo, emissivity, all these have to be consistent. Because if you are not dealing with consistent, just like now, the Wolf have been giving you, they are not consistent physically, then you got in trouble. I didn't have the time to show it. But some, for example, the albedo change regression, they supposedly observe that they should be linear increasing with the observation, but they actually reverse. So how are you going to use that to study your climate change when the land cover being removed? So again, these are very tough problems we deal with.
Another question about the lateral boundary condition.
Yes.
I think you forced me with the reanalysis data, right?
Yes.
And is it sensitive to different reanalysis?
Yes. That's a very important problems.
How
Yes.
important is it compared to the surface condition, surface boundary condition?
Yes. Okay. So I didn't have time shot. This is a big topic. So at the very beginning, we first get the surface boundary condition right. The second way is get the lateral boundary condition right. Then you will go back and talk about physics. Because if these two pieces is wrong, you focus on physics, so you're not going to have any good sense. So we spend a lot of time around these edges. So currently, when you run the Seawolf with NRI, I'm very unhappy with my just 100 meters away now, the building from my building, the NCP's product. So the analysis, when you're driven, the analysis is not this model, CM5, a mini model, their results is very bad. So you start with, is my regional model is bad or with a global analysis is bad? So we using the ERI, which is currently we find the best reanalysis products that we can have. And then we get beautiful, the precipitation over the Rocky Mountains, the precipitation over the southeast, the Midwest, all match with observation very well. And when you check the circulation, the ECMWF do very well. But we still have an issue. I cannot answer rigidly that ERI is really everything better than NCP. So that I have to say. But at least from all our understanding, the ERI make much better. Now, and also I needed to add in another one. So for the 2012 drop versus 2011 drop, which is a big topic now in our north. So people want to predict the 2012 drop. And we use the NCP as a real prediction to drive the Seawolf. We cannot predict the precipitation. We remove many of the over devastating precipitation. This is supposed to shouldn't have a precipitation. The NCP give a very large precipitation amount, so that causing the drop is not there. We did remove about 50% through our regional capability. However, the trend is still not dropped. So what then we use the ECMWF reanalysis to drive that. The ECMWF reanalysis did the precipitation, predict the precipitation is drier, okay? But then we're using that and we nail the drop event very, very beautifully. So that gives me confidence that the physics we put in the Seawolf is appropriate in the time for the tendency. And I also need to answer your question. It's not all my results shown here is driven by the analysis. We verify the system, the regional model performance driven by the analysis. That's all. But for all the application, we're driven either by the real prediction, the weather prediction, forecast results, all the seasonal prediction in 6 months lead time. Okay, and all for the climate change study, we use fully coupled NSSSM, UK Met Office, all these CFD to drive it. So it's a predictable.
Yeah, back to the comment you had. In a sense, your super ensemble is really just tuning your model because there are so many unknowns and also a lot of unknowns of observations.
Mm-hmm.
So in your prediction, I notice you're not in what we call forecast mode in the sense you are, doing a hindcast. So given the fact that what you have adjusted, and the physics may be right, may not be right, that's nobody can control, as the example you just gave. So my question, have actually tried to do the real forecast, given one, instead of trying to predict, because the part you have has always been the case that been used as part of your tuning by the work. So that's kind of questions.
Okay, so first when I show you the CFS, this is a real prediction, not hindcast. So even though we go back, but we use, this is everyone agree in so-called MECA, I'm sorry. This one actually use the CFS to predict results. Okay?
So this time period is actually not within your, what I use the word tuning.
So it's not like a tuning at all. We verify that and then using the predictive mode to show that if that time, because these are the historical, the CFS put on the web, we're using their real prediction to do the downscale.
But this you have the same problem because you also use the same period when you were doing your model.
There is no tuning here. This one do not tune. This is just run the wolf and go ahead. There is no tuning here.
Not really. Let me see. Maybe I misunderstand.
Okay.
Because your model has been developed
Right.
using.
Oh,
the same
okay.
data.
I get your answer. Okay. So optimization have not been put into this. You can see I'm using just the run individual. Okay. The different.
So this you just.
Yeah, if I make the optimization, I will improve much better. Okay, I didn't. This is just individual, but I only show here at that time it's 4, and we have 15. Show the same. This is very better. So this is not. So what is optimization? In the paper, we're not done that. Optimization actually done use so-called cross-validation. You take out a certain chunk of that and build the optimization with the rest, and then using that to forecast the things you take out. This is normally being used by mathematicians called cross-validation. And in the real time, for example, now we are building so-called real-time operation. For the weather one, I shall just briefly say that we use the last week. So we assume the weather systems carry the memory. So we use the last week's forecast error to devise this weighting. And then using that weighting, don't change forecast next week. And then for the seasonal climate prediction, we use the earlier 10 years performance to build the weight, and then using that weight to carry for the next. And the furthermore, which is what I want to do if I have the funding to do, is that the so-called device dynamic weighting. And we already analyzed, for example, Greenfield scheme versus gray. The weighting function is very stable and large scale. They are not local scale. For the two schemes we work with, Greenfield and gray, actually that weighting distribution happen to be very closely related with biochemicity. So the gray scheme work very well when the biochemicity is very strong, where the coupling with upper jet stream with a low jet stream in the Midwest is a phase not there. But for the temperature is reverse, so more like a K. So there is a certain physics is behind these routine because originally they derived. Does that answer your question?
Sure.
Okay.
Heidi, do you have a question?
Yes.
Have you compared in the observation?
There is, unfortunately, there is no observation because the soil moisture is a big problem. Satellite alike, we do not have the soil moisture work. But for Illinois, we know there is a strong coupling and the model show better. And I have a correlation type on, and the other one don't have the correlation. But it's very limited. And then I hope the satellite will give us better information later.
Okay, so there are no more questions, so let us thank Professor Liang.